All right. Yes, it is my pleasure to be here. I'm very excited to present on this. I joined the AWS Rust SDK team several months ago, almost half a year now, and I've been helping them build it. And I've also been presenting on it a little bit. I presented at reInvent last December. For anyone that's not familiar, AWS stands for Amazon Web Services. So what am I going to cover tonight? We're going to look a little bit at how to use the SDK to send a request to S3, which is our simple storage service. We're going to look at what actually happens with that request as it's getting sent. We're going to talk about how we actually code generate all these SDKs for 300 plus services. It was 316 different SDKs that we produced the last time we counted. And we're also going to talk a little bit about what you can do if you're interested in contributing to the SDK, because it's all open source. And then, of course, at the end, we're going to have time for questions and answers. So to start, making a request to S3. Now, there's a lot of extra context for people here. I've shared these slides in this Meetup's Discord channel so that people can click on all these links. Because every few slides, there's going to be 4 or 5 links for you to take a look at. I've linked here are 2 repos, one for the SDK and one for the code generation repo. I've also linked our repo that contains all of our official examples. I've linked the developer guide that we put up a little while back. I've also linked our crate documentation, so you can just jump right in if that's what you're interested in. Now, we only have a limited amount of time, right? So there are a couple things I'm not going to be covering in this talk, and that's going to be stuff like creating an AWS account, how to get and store your access keys, how to create a new Rust app with cargo, or I'm not going to talk about how to do async runtime stuff with Tokyo specifically. We're going to be using it, but I'm going to kind of gloss over a lot of the basic things. However, again, I have included links to all those things. So if you're not familiar with any part of that, you can go click the link and get some more information. So first things first, we want to make an app that interacts with AWS. Now, whenever we're doing stuff with the SDK, it's pretty much all happening async. We use Tokyo a lot, although technically the SDK can be runtime agnostic, which I'll talk a little bit about later. But in this example that we're looking at, we are defining our main function. We're saying that it's fallible, that it might return an error. We're initializing logging, which is always a really good thing to do. We have a lot of logging set up in the SDK to help you understand what's actually happening. And the first real thing that we're doing here is on line 5, we're creating a config, an SDK config. Now, an SDK config is responsible for collecting all this information from your system and making it available to the clients that we're going to use to make requests later. Every client kind of has its own needs, but there are a lot of shared things that they need to know about, and all that is encompassed in this struct. And all we have to do to create one is call AWS config : load from end, and then await that, and that's it. This will read your environment, your file system. It might even make calls to like fetch credentials from remote sources. And it does this by looking at things that are the same for every single AWS SDK. So if you've already set up your computer to work with another SDK for AWS, like the Python SDK or something like that, then this is kind of like a drop-in replacement. You can just run this and it's going to load all that configuration from your environment. So next, we're going to create our client. Specifically, we're going to create a client to talk to our simple storage service. Now, I may have mentioned earlier, simple storage service is for storing objects, basically just any data. And it organizes that data into buckets, and you refer to that data with keys. So here, we're creating our S3 client. And all we have to do that is to pass it that shared config. And then that's it. We now have a client. Next, we're going to use that client to create a builder function for our request. All requests in the SDK get constructed by these builders, where you say what builder you want, you call methods to set any inputs that it might require, then you call send, and that's going to turn it into a future, which you can then await. And then because this is Rust and because these requests might fail, you'll see that we have that little question mark try operator at the end, which if an error occurs, it'll bubble it up and then get emitted. And that's it. Like you can create your config, create a client, make a call in just 3 lines like that. For most users, it's going to be this simple, and we're really proud of how easy we made that. Of course, it's not really that simple, right? Like a lot is actually going on. So what's really happening under the hood when we do all that? Well, first, looking at that config, what we call load from env, what that's actually doing is it's calling this function called from env under the hood. And from env makes this thing called a config loader. And the config loader is responsible for doing all those things I talked about, looking at your environment, looking at your file system, and so on. And then it just calls load on it. And that means you get all the default behaviors from it that you would normally do. We're not overriding anything or replacing anything from the environment. And then we just immediately await it so we can get our config back. So you can manually create these config loader structs, but really you shouldn't need to. It's best if you use load from env and just rely on storing all your config in your environment as opposed to setting things manually in your program. However, if you do need to do that for testing or because you think it's going to provide a better experience for users of your app, then that is okay. So the config loader sets all these different things. It collects information like what your app's name is, which we use when logging things and making requests. Your credentials provider, basically like, are your credentials for AWS coming from your local environment? Are they getting loaded in one of the standard ways that we have for doing that? That sort of thing. We also have an endpoint resolver. That helps us know where to send these requests because AWS is really big, right? And so this will figure out exactly what URLs to send each of our specific requests to. And again, you can override that if you need to test. And you can actually point it to local stack, which is sort of like a local testing version of AWS. You also have to provide a region because AWS is regionalized. When you set up something like S3, you put things in specific global regions. And that's basically an abstraction over the location of these things. Stuff that's closer together will run faster than things that are farther apart because that's the internet. You can also set retry and timeout related stuff here. And that's just, basic things for making an HTTP request. An interesting one in between those two is sleep. And so earlier, I mentioned that we're kind of agnostic over async runtimes. So this is how we can achieve that. At the very lowest level, what we really need from an async runtime is the ability to thread sleep, the ability to say, wait for this amount of time, and then tell us when that time has elapsed. We need that for retries. If a SDK is getting throttled because you're sending a lot of requests, we have to be able to wait. We have to be able to see when a timeout has elapsed. And so by allowing people to supply their own thread sleep function based on whatever executor they're running their program on, then this will allow everything to still just work. We also have a provider config. That is our abstraction over things like your environment variables, your file system, things like that. And that's really helpful during testing because in testing, you want to be able to run tests in parallel probably. You don't want them to all be setting stuff in the actual environment and overriding things. You want to be able to set a specific, consistent, environment for each test. And so we do that with the provider config. And then lastly, we also want the SDK to be generic across HTTP frameworks. Right now, it's pretty heavily based on Hyper, but we're slowly adding the ability to switch out different parts to use whatever HTTP framework you think is best for your needs. Okay, so that's a lot of information. Like, where does that even come from? Well, it gets set mainly in 2 ways. These kind of very simple config structs where it's just saying like, hey, for this, just insert this small piece of config into the larger shared config. It's just structs filled with data. Determining default values in this case is really simple because they're either just hard-coded things or they're just left unset. But for really complex things, like credentials and so on, we use these things called providers. And provider is some sort of trait object that optionally returns one of those config structs. And we box or arc them so we can pass them around, but not worry about ownership. So one of the cool things about providers is that we're able to chain multiple providers together. And so one example of doing that is, like, say we want to get your timeout config. You could define that with environment variables. You could define that in your AWS config file. And we have to look in all those places to understand how to do timeouts that you want, right? And so what we do is we make a separate provider for each one of those situations, and then we chain them together into this kind of super provider. And that's what we use to figure out how to set your settings. These are great for when determining default values is very complex, because we have to look in multiple places, or because we might have to make async calls. We might have to call some sort of service that will provide the credentials on the spot. And that's basically how all that stuff works. So I said earlier that you generally don't need to override these things, and it's best to set them in your environment. However, we do, of course, provide the ability to do so. So in this example, we're doing from env instead of load from env. And that allows us to modify this config loader before we actually use it to get all that config from all those different places. And in this specific example, we're saying use the default region provider, and it's a chain, so it's going to look in multiple places to figure out what region you want to send requests in. And then we're saying if they haven't set anything for that in any of those places, we're going to fall back to the US East 1 region. One thing to be careful of, and a mistake that we see sometimes, is that when you're overriding these things, you have to make sure that if your provider that you're inserting here might not provide something, then you should probably combine that with the default provider, right? Because if you get rid of the default provider, then there's a chance that you're not going to set anything here, in which case the SDK is going to panic, so that we can bring your attention to this as early as possible, because we can't send requests without these things generally. Okay, so further under the hood, all services that make up AWS, they all have their own config struct that implements the ability to convert from a reference to that shared config to a services specific config. So why do services need their own config? Most of them are exactly the same as the SDK config. However, a couple services do have these service-specific options that they need. And by creating service-specific configs, even for services that don't need them, it allows us to preserve backwards compatibility if they need to add those service-specific things at a later point. One example of a specific thing is that our Elastic Cloud Compute service, EC2, requires an item potency token to be sent with a lot of different requests. So when creating a service client, the client new method takes that reference to an SDK config. It's calling that from impl under the hood to convert it to a service config, and then storing that within itself. And for testing purposes, it's totally possible to create a client directly from a service config and an HTTP connection. And we're going to kind of look at that a little bit later. And there are two main things to focus on. There's a lot of text in this area, but what's really happening is that we're setting up some kind of middleware, and we're setting up some kind of Smithy client. What is middleware and what is a Smithy client? We'll talk about that in a second. But what this code is doing is it's taking a service config that we got because it automatically got converted from us, or for us. We're looking at the retries, the timeouts, the sleep implementation, things like that. We're setting up this thing called the default middleware, and we're putting that all together in this builder that eventually produces a service client for us. And that service client, you can see it has that arc and there's a handle inside it. We're also going to talk a little bit more about that in a second, what's actually happening there. So before we get too far ahead, what is a middleware, right? Not everyone is a web programmer, so they might be unfamiliar with this term. Middleware is basically a way of defining reusable behavior for either your client or your server. And sometimes it's general purpose behavior. Sometimes it's more application specific. So a general purpose thing might be like logging or something like that. And a more specific thing might be some form of request signing. So you would set up a bunch of middlewares, one on top of the other, and then it's like a pipeline that you can send a request through or that you can send a response through, and it will inspect it and modify it as needed. So at the end, you have a request that's ready to be sent off to some service, or you have a response that's been processed in whatever way your app requires. And then Smithy is the name of the language that all of the AWS services are modeled with. Smithy RS is our specific code-gen tool, or rather collection of a bunch of tools. But Smithy itself is kind of the whole thing. It's the modeling language itself. Okay. So all services right now use the same middleware stack. We have basically like a couple of default things that we're always going to need when we're making requests to Amazon stuff. So that includes like that endpoint resolution, which we talked a little bit about in the config thing. Like config will set all the logic for how that happens, and then this will set up the thing that will actually figure out where stuff is going at the time we send the request. It'll allow us to insert user agent headers into requests. It will allow us to sign requests and basically set these authorization headers, which are sort of like credentials. Technically, they're not, because sending your actual credentials in a request would be unsafe. And that default middleware, it's just what I said. We're setting up these layers. And so these different layers, we've defined these specific ones, but they're very generic, and they're based off of this lower level framework called Tower. And Tower is just this general framework for defining services for HTTP stuff. And the service can like literally be like you sending requests to something or something sending requests to you. The abstraction fits on both sides of the sender and receiver kind of thing. In our case, we're just sending and then we receive. But yeah. So I mentioned a Smithy client a little while back. I've also talked about service clients. Those are different things, and it can be kind of easy to get them confused when you're very new to the SDK. I know it was a little hard for me at first. Service clients are actually a wrapper around that service's config that it needs, and then like a pool of actual HTTP clients, the Smithy clients as we call them in this. And a Smithy client is a Tower service composed of a bunch of different layers. Again, just like the middleware. It's actually almost the same thing. It kind of looks like the same thing, except it has a couple of extra things like timeouts, retries, how requests get dispatched, deserialization, things like that. And we're going to look at that in a little bit. The takeaway is that Smithy clients consume operations in order to send an HTTP request. So under the hood, dispatching an operation. So this is like earlier when we had that list buckets thing and then we did send. Under the hood, we're dispatching an operation. So requests made to a service are represented as operations. In the model, like this actual Smithy model, the word operation is a shape, a kind of thing that associates inputs and outputs and request-specific errors. And in the SDKs, we have a type called operation, and that gets created from an input sent by a client, and then either the output struct or an error struct is returned in a result. And the function that we use to turn that input into an operation is, unsurprisingly, make operation. And it does that actual conversion. It makes the operation, which inside it contains an actual HTTP request, which is like a specific Rust library, the HTTP library that pretty much all web frameworks in Rust are based on. Yeah. So operation construction. When we're creating that service client, that's like setting up the config, setting up the middlewares like we talked about. The next thing that we do is we call an appropriate method to create a builder. So in our first example, that was list buckets. And that starts building a list buckets input, which is going to be used to create that list buckets operation. And importantly, that builder inside it has a handle to the Smithy client. So our service client created this thing that has all the information needed to send a request, and it copied or gave a reference to its internal HTTP client so that request can just be sent at its own leisure, or rather at your leisure. So next, we set all the required configuration for that builder and then call send. So in the list buckets example, we didn't actually have to set any different things, but we're going to see an example in a minute where we do set a couple of different fields, and it all happens through calling methods on a builder. Next, after send is called, the send method is responsible for building the input struct from all those different things that we just set, and it converts that into an operation with make operation. And that's where you'll get an error if we can't construct an HTTP request, which is, I struggle to think of a situation where this would actually happen. It'll pretty much never fail. But if there was something wrong with it, if something caused the request that was created to be invalid, this is where you'd see an error, and it would tell you what you should do about that. Then the send method will pass this new operation it's just created to a Smithy client's call method. Okay, and so I've produced a couple things here so we can see like what send looks like and what happens with like operation construction. So here we can see a send method for list buckets, and we can also see that it's calling build. That's where we're actually getting that input struct. It's mapping the error into a construction failure just in case there's an issue with that. Then we make an operation by passing it config that it needs to understand how to make an actual request. We wait for that to finish because sometimes creating an operation might require some async something like reading the file system or sending off a request. And then we also will map that error into a construction failure. And then at the end of that, we have our operation, and we pass that to that client that we have, the Smithy client, not the service client. Okay, low-level tangent. Like, we keep going deeper. I'm going to go a little extra deep for a second here. Okay, we can do a lot of this stuff manually. When we did it the nice way, it was 3 lines, right? And it just worked kind of magically. But for testing, we often do it the more difficult, specific way because it lets us override a lot more. So in this case, we're building a service SDK directly by getting the config builder, setting a credentials provider with like hard-coded testing credentials, setting the region to always be US East 1. We're creating our own HTTP connection and injecting that into a service client's new thing to create a, well, actually, sorry, I misspoke. Here we're actually creating a Smithy client. So normally we create a service client that has multiple Smithy clients inside it, potentially. But here, we don't even need that. We're just going to create our Smithy client directly. Then we create our operation manually. So we have our input here that we're saying, this is for put object, by the way, not list bucket. So we're calling builder methods on it. We're saying, I want to put an object to my test bucket. I want to name it key.txt. I want to, it has this body of some test text. So that's what we're going to upload as the actual object. Then we call build. That takes that builder that we just constructed, turns it into an input. And that could fail, but since this is a test and we know it's not going to fail, we just unwrap. Then we call make operation on that resulting input, and we have to pass the service config into it, just like we saw was happening for us when we called send originally. And we have to await that, just like I talked about before. And then next, we do a cool thing that we do in testing, where we can actually take that operation before sending it and insert certain hard-coded things. So like we hard-code the date that the operation is getting sent because we're going to check the request at the end of this test, and we don't want that check to fail because the request was sent later than the first time we did it, right? We want to hard-code this stuff so that our tests are repeatable and consistent over time. And we also insert a specific user agent for testing. Then we call the call method ourselves. So everything that I've just covered, all of that happens automatically when you call send. But as you've seen here, if you have specific needs, normally testing, you can kind of do the harder, more verbose version and switch out any part of it that you need for whatever purpose you have. So when call happens, a lot of interesting stuff is happening in there too. We actually create a new tower service whenever you call. And it's basically its own server that has one job, just to send your request. And that's it, nothing else. It will modify that request by passing it through a bunch of different layers. And then it will actually dispatch it, send it over the wire. And then when it gets the response, it's going to deserialize that either into the successful struct or some error, right? And return a result to us. Now, errors can happen for all sorts of reasons, things like a connection issue, or maybe there's DNS issues or socket hangup, things like that. Or it could be the service responding with an error, like, hey, you're sending me too many requests, or you forgot to set this required field in your request, or the thing you were looking for told me to look for doesn't exist, stuff like that. And so inside that call method, this is what it looks like when it's constructing that service. It creates a new service builder. It adds timeout layer. It adds this layer for retries. It adds another timeout layer because we actually add one layer per kind of timeout we support. We support multiple kinds. It adds a layer that will parse the response into some actual Rust struct when it comes in, or an error, hopefully not. It inserts that middleware that we created earlier and stored in our services config. It creates this dispatch layer, which will take our operation request and actually dispatch that request over the wire. And then lastly, we define that connector, which if you're doing this automatically, like if you're doing the nice 3-line config client send version, that connector is going to be determined for you. It's going to be based off of Russell's Rust TLS, or like a native cert, some sort of HTTPS connector under the hood. And we basically pick that for you, although you could replace it if you wanted. And then in that testing example that we saw, this will be that test connector. We actually have a bunch of really cool test connectors for this. Like we have one that will inspect every request you send with it to make sure that it looks the way you expect, and that will respond with these canned responses so that you can make sure that your app always handles the responses in the way that you want. Another cool thing, though, is that like when we create this stuff, because it's creating a new service stack, we don't have any confusion about like if we change the configuration, is that going to change what's going to happen with my service before I send it? Like, you don't worry about stuff like that because this has all of that state contained within it, and it's perfectly ready to make that request at any time. And you can make a bunch of these services just on the fly, which really surprised me when I first started out. I thought it was like kind of weird, but it's actually really cool. And that's it. After only, I don't know, like 1,000 steps, right? We've actually sent a request. And it's great that like all that can be so easily expressed in just those 3 lines. So that was a lot of Rust code we looked at, right? Like, where does all that come from? It's got to come from somewhere. I said that there were 316 services. I'll tell you, we don't write it all by hand. We have to code generate it, right? So how do we do that? It's Kotlin. We use a bunch of Kotlin, actually. We had considered using Rust for this, but all the canonical tooling for Smithy, which is a pre-existing thing that all the other AWS SDKs are based on, all that tooling is written in Java. And so in order for us to like just get started right away writing this SDK and getting it out to people that need it, we decided that it was a better idea to take all these great things that already existed and build on top of them rather than try and replace them. which is a lot of Rust developers. We always want to rewrite things in Rust, and there's definitely a bit of a desire to do that sometimes. But we have really benefited a lot from being able to use all these existing things. And it frees us from having to update and maintain all those tools, which is the real secret. So, like, how does CodeGen work? Well, we talked a little teeny bit about Smithy earlier and how we use that to define our models. Our CodeGen will look at those models and turn them into REST. So it will look at Smithy primitives, because Smithy has its own way of defining integers and strings and things like that, and turn those into Rust primitives. It will take all those Smithy shapes, which kind of look like Rust structs, and actually convert them into this abstract thing called a symbol, which then gets converted into a Rust struct. And one of the cool things that we do with this is that in Smithy, not all operations are defined with both an input and an output struct. And we're going to look at a model and talk about this in a little bit more detail later. But because of the way that CodeGen works, we can prevent backwards incompatible changes based on people adding new things. And I'll show you exactly what that looks like later. We define these writers, which are basically super-powered string formatters to create files and insert this Rust code into them. We also have things that will create Rust crates for us and manage the dependencies of those crates. We have all these things that will set up serialization and deserialization for all these models so that we can send requests and interpret the responses that come back. It also controls how these service clients get created with all their different operation builders and how their config works. And it also sets up the CodeGen for those specific operations, like how they actually work inside. And then also we have kind of the flip side of this, or rather another layer on top of it, which is AWS specific stuff. So Smithy is actually this generic framework that anyone can use to define any kind of service, not just one that you would see at AWS, but there are other companies that actually use Smithy to define their own services and generate SDKs for those services. For AWS services, that means we need to add a couple of special AWS specific things to our CodeGen. So this is like support for signing our requests. As I talked about earlier, adding user agents to requests, adding AWS specific fields to like service client configs, adding license headers for Amazon to all of our generated files, generating our READMEs for each crate, and then inlining something called Inlineables, which is not too descriptive, but I'll explain what that is in a moment as well. So I've been talking about models. We haven't actually looked at one. This is what they look like. You can see that this is the model for that list bucket request that we sent at the very beginning of this talk. And it defines an output, which targets some sort of shape, in this case, the output shape. It also has a couple of Smithy traits, like one for documentation. We actually read that documentation and output that in the crate so that when you go to docs.rs, you will see that documentation. And it also says that this is an HTTP operation where we're supposed to get from a specific URI and that a success response is going to be a 200. And so just looking at that is enough information for us to generate this call to list buckets. You'll notice here that it doesn't have an input struct. That's because list buckets doesn't take any input. It just shows you all of your S3 buckets. Now, the thing about that is that in Rust, when you have a function signature with like inputs and outputs, you cannot change that signature without it being a breaking change, right? Like if we added a new parameter to a function and then you update it to that version, that would break your code and stop it from compiling. And we don't want that to happen. We really don't like breaking people. We don't ever want to have to do it. And so in situations like this, it's possible that they might add an input in the model in the future, that the S3 team might modify that model in that way, because for them, that's not considered a breaking change, but in Rust it is. And so what we have to do is we will generate a synthetic symbol. We'll pretend that this has an input that just has nothing in it, just so that we can make sure that when we make these function signatures, that they will never change, even if they add stuff in the future. And there's a couple of more links in here. I link to where all of our Smithy models are. I link to the traits that you can use to customize like a specific model and better explain what it does. Smithy models are defined in either the Smithy language or JSON. In our case, we consume JSON files. If we wanted to do the other way around, we'd have to write an extra thing. But all AWS services are currently output as JSON Smithy files, so that's what we use. So that step that I talked about, just reading the model, that's not exactly quite enough to make a working SDK. So we have all this other stuff too. We have shared types across, all Smithy services that they would need, usually related to HTTP stuff. Other core HTTP things like what an HTTP body is, utilities for setting, modifying headers, things like that. We have our byte stream struct, which is our abstraction over any streaming collection of bytes. So you'll be using that anytime you send a request with a body or receive a request with a body. We have that service client based on Tower that we talked about earlier. We have other utilities abstractions that are kind of, they're not just SDK specific, and they're maybe not even runtime crate specific. They're just used across all of our runtime crates. And we also have the actual code for serialization and deserialization. It's very generic, and that gets put together when we're generating SDKs. And we also have our AWS specific ones. Again, just like with CodeGen, our runtime crates have those two layers, Smithy and AWS. And so this is where we actually define our AWS specific types, where we define how the shared configuration works for all services, where we define how that endpoint resolution occurs, where we define our middlewares and how request signing happens and everything it needs for that. And I glossed over this earlier, but we also have Inlineables. So the general thing is that we want to avoid writing Rust within Kotlin as much as possible, because it's not very easy, right, to do all your coding in a string. We want nice like IDE support, and we also want it to be easily testable with existing tools like Cargo and so on. So what we do for that is we have something we call Inlineables, which are Rust files that can kind of exist on their own and have tests, but then at CodeGen time, we copied over into that generated crate so that that crate can use them. So that was a lot of stuff, but that is about as deep as it goes. And the core thing to remember is that it's all layers. We have multiple kinds of configuration that all get collected and passed through. We have an operation thing that gets constructed, which gets turned into an HTTP request. And then all that configuration and the request go into some sort of client, which sends the request and receives the response. And we try and write as much of that in Rust as we can. But for stuff where we have to look at the model, it's all code generated. So if that sounds interesting and exciting to you, I would love to see contributions from all of you to the SDK. It's all fully open source. We love getting feature requests from people. We actually prioritize our feature requests based on the number of thumbs up they received on GitHub, because it's very important to our team to make sure that like we're building things that people that want to use AWS need right now. We love PRs. We have a contributor guide that I have a link to in these slides. And we also accept requests for comments, or RFCs, as we call them. And an RFC is a document that's going to propose some sort of change, either to like our code generation or to the SDKs. We write these all the time on the team for large or complex changes, where we want to make sure that they get really good review, because it's not enough for us to build something that works. We want to build the best solution that we can think of that works, one that's really easy and simple to use and understand. Anyone can submit an RFC, and we have a template to help you get started writing one. But if you're afraid to maybe start writing one right away, that's totally okay. If you want to just start by filing an issue with us or starting a GitHub discussion, that's totally cool. Okay, and now it's time for Q&A.